Bernoulli's equation, couple of applications of the same. So today we will look at most of the applications and problem solving aspects with Bernoulli's equation. So let's begin. Right. So the last thing we had discussed in the previous lecture was the application of Bernoulli's equation in a situation where you have variable cross-sectional area of a vertical pipe. So the pressure difference is affected by the difference in kinetic head because of the area being different. So continuity equation, as well as the difference in the gravity head because it's a vertical pipe. So let's look at further applications of the same. So Bernoulli's equation, the statement was that if we compare any 2 points in a pipeline through which fluid is in an ideal fluid is in steady flow, then we can compare the velocity of flow with respect to the pressure at those 2 points where the cross sections are A1 and A2. And with respect to some reference level, if the vertical height of these 2 points are also H1 and H2, then we can compare these by saying that the sum of pressure, kinetic energy per unit volume, and gravitational potential energy per unit volume with respect to that reference level is the same at both these points. This is one way of expressing Bernoulli's equation, or we can simply say that you select any point, the sum of these three quantities, the pressure plus kinetic energy density plus gravitational potential energy density, is a constant. Now, on the other hand, we have already seen the continuity equation earlier. So that simply states that the volume rate of flow or the volume flow rate is uniform. So if we compare 2 points, the product of area into speed of flow or velocity of flow is constant. Or we can just say that the volume rate is uniform throughout. So these are the two mathematical equations that are used for solving any and every situation in hydrodynamics. Okay. Of course, remember that they are applicable for steady flow of an ideal fluid only. So let us start with the one of the common applications of these equations. Okay, that is in a physical apparatus called the Venturi meter tube, or simply Venturi meter. So this is an apparatus used to measure the flow rate in a steady flow situation. So it works completely on the principle of application of these two quantities. So let's understand it in detail. So the basic apparatus of the Venturi meter consists of like Let's say this is a cross section of a pipeline through which a fluid is flowing. Then there is a change in the cross sectional area. So it has a region where it becomes narrow. Then again it widens back to the original shape. So if now what we do here is in this region now two narrow pipes, vertical pipes are inserted. Now let us say a particular ideal fluid is in steady flow, and these roughly represent the streamlines. Yeah, I got disconnected. Yeah, so coming back to this, so if we have a fluid in flow, and if we are to compare a point like this over here, where the speed of flow is V1, with another point over here with the speed of flow is V2, because the area of cross section here is capital A2, and the area of cross section here is A1. Now we can see that the 2 points that I've selected are lying on the same horizontal line. Okay. But because there's the speed at this point is more, the pressure will be less. So the higher pressure in this region will cause liquid to rise to higher level. And by measuring this level difference, we can estimate not only the pressure difference, but we can then write a formula to understand the flow rate of liquid over here. So if I select this point as my point 1 and this point as my point 2, and this is an ideal fluid of density rho, which is in steady flow like this, then comparing the 2 points, I can see that half rho V1 square plus P1 should be equal to half rho V2 square plus P2. Okay. Their heights are same because they are the same horizontal level, so that factor cancels out. So this pressure difference P1 minus P2 is equal to half rho V2 square minus V1 square. This is our first equation. Okay. And then second, we also have that A1 V1 is equal to A2 V2. So we can write B1 as A1 by A2 times, so V2 as this. Okay. Now suppose this area of cross section K1 is n times K2, where n is a known quantity which is greater than 1. So then V1 becomes V2 by n. So this equation here, so this is our second continuity equation. This one, our first equation was Bernoulli's equation. So making use of this, we can see that this pressure difference is half rho V2 square into 1 minus 1 by n square, because V1 is equal to V2 by n. Okay. Now we can also see by comparing these 2 points with respect to the vertical column, you can also see that P1 is equal to P2 plus rho GH. This height difference is H. So this is coming from our vertical pressure gradient. So this pressure difference is rho GH. So substitute this here now and we get so this now gives us a formula for calculating the speed of flow, which is kind of factor, or the volume rate. We want to calculate that. So this is the working principle of this kind of device, which is called a Venturi meter. It works on the principle of application of Bernoulli's equation and also vertical pressure gradient. So just make a note of this. No, Diti, the pressure is greater at the point 1 because the speed is less. Na? So Bernoulli's equation clearly says where the kinetic head is less, the pressure has to compensate by being larger. You can understand volume elements of liquid are accelerating as they go from 1 to 2. So the pressure from this side has to be more. It's counterintuitive. One thinks that if it is narrow, the pressure should be greater, but it's actually not that way. And that is what Bernoulli's equation tells us.
done some
Okay, so that's the application for Venturi meter. Now the second application of Bernoulli's equation, which is very standard, is the application for the concept of efflux or velocity of efflux. So when we have a large cross-sectional area kind of tank, and there is a small opening or what is called an orifice, somewhere near the bottom of the tank, then liquid comes out in a like a thin jet. Okay, and that process is called efflux, the opposite of influx. So the speed at which the liquid is coming out, that is called the velocity of efflux, or speed of efflux. So there is an orifice here, so it's a very narrow opening. Let's say its cross section is small a, whereas the tank's cross section is capital A. So A is extremely small compared to capital A. So that kind of situation. So then liquid will be coming out from here. And depending on the level of water in the tank, the pressure difference will create this efflux speed. Okay. So this is called the velocity of efflux. So now the derivation of that is done using again a combination of Bernoulli's equation and continuity equation. Everything in hydrodynamics is always ultimately a combination of these two things. So what happens here is that to understand the speed of efflux, what we do is we visualize the streamlines. Because of the effect of gravity and the pressure difference created by it, the liquid tends to flow in streamlines, which are like this. You can see that there is a very high concentration of streamlines because the orifice is very small in area compared to the tank. So now if we take the point just outside the orifice as 0.1 and we take the point just at the surface as 0.2. So this point has a velocity, let's say v2. Now we apply Bernoulli's equation to these 2 points. So we can see that pressure at the point 1 is equal to atmospheric pressure because it's just outside the orifice. So it's in contact with open atmospheric air. Pressure at the point 2 is also atmospheric pressure. So it's an open surface. And the height difference between these 2 points is equal to the height of liquid. Okay. And we also have that efflux velocity into this area of cross section is equal to V2 into capital A because this area was capital A, this area. Okay, so now V2 is A by A times E. So V2 will be negligible or very small compared to the efflux velocity because E is very small compared to capital. Now applying Bernoulli's equation, P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square. plus rho g h2. Now in this equation, we will substitute all this information that we have written here, that P1 is equal to P2, equal to atmospheric pressure. Okay. Rho g h2 minus h1 will be equal to rho g h. Okay. V1 is equal to the efflux velocity and V2 is negligible compared to the efflux velocity. So we will now get this kind of relation, that half rho efflux velocity square minus V2 square is equal to rho g h. So now because of this, we will be able to neglect V2 square compared to VE square. So we can say half rho VE square is approximately equal to rho g h. It gives us a very interesting result, that the efflux speed is like a free fall speed through a height h, where h is the level of liquid inside the tank. But this is of course subject to the condition that the area of cross section is very small compared to the area of the tank. So it's a small orifice. This cannot be the value for a large opening or an opening such that the area of cross section is comparable in area to the area of the tank itself. It is a very specialized result for an orifice, and that only in a situation where liquid is coming out from an orifice, that is its area of cross section is very small. In that case only we call it velocity of efflux. So this whole derivation is based on that principle. Okay. So you have to know this formula for direct application, and of course you have to know the derivation of this by Bernoulli's equation and continuity equation. Both the things have been used here. Just make a note of this.
Excuse me, sir. Excuse me,
Yes, what happened?
sir. Where is PO here in
Huh?
the where is PO is in this apparatus?
Atmospheric pressure, beta. Outside the
Okay, okay, okay.
atmospheric there is pressure. That's why the explanation is also written over here. It's an open surface. It is just outside the orifice. So it's
Yeah, yeah, yeah.
atmospheric
Got it.
pressure.
Okay,
सर
sir.
वो
Done, sir. Sir, done.
Yeah, students, I was just disconnected. So let's get back to the lecture. Okay. So yeah, we were discussing about speed of reflux. I think you have finished copying this down. Okay, so let's look at, so both the applications, major applications we've discussed about. One is the Venturi meter situation, and the other is the speed of reflux concept. Okay. So let's look at some application questions based on this. So one type of very common problem at JEE level, find questions like this plenty in HC Verma also. Let's say we have this tank which is kept on a horizontal table like this, open tank with liquid filled up to a certain level. Now what we're doing is, instead of making the cut or the orifice right at the bottom, we will make an orifice which is somewhere on the side like this. So now this is where our orifice is. So it is at a certain depth, let's say D from the top. So the liquid comes out in a sort of horizontal jet like this with efflux speed, and a thin jet of liquid now, as it is gushing out, it also achieves a horizontal range. So this range is, let's say, capital R. So this is water. So suppose H is given to us as 40 meters and the depth D is 30 meters. Find first of all the speed of efflux, then the range. Take G as 10 meters per second square. So just try this question out, people. I hope everybody is online. Yeah, looks like more or less. Okay, so I will start giving you the steps in a minute or two. Okay, just understand how you will apply the concept of velocity of efflux that we've seen in the previous section to find the speed of efflux. And once you've got that, the rest is like a projectile motion. The liquid coming out is like it's getting horizontally projected. Okay, and its motion is purely motion under gravity. So something horizontally projected and being pulled down by gravity will follow a parabolic path like that one. Okay, so anybody got the answer for the speed of efflux? So here you can see that the efflux
Sir, 2 minutes.
speed. Achha, you're working it out. Okay.
Yes, sir, we are working.
Okay, send me the answers on text, please.
Yes, sir, sure.
Yes, your answer is correct for speed of efflux. Arvinda, you have to check your answer once more.
Okay, sir.
Okay, so let's work out the answers. So the speed of efflux here will be root 2 GD. Because again, see, the thing is you are comparing this point with this point. Na? So the height difference between these 2 points. So again, it's the same thing. Na? You're applying Bernoulli's equation that way. So this water that is below this level does not contribute to any efflux. It's only above that contributes. So you can see it's this. Okay. So the speed of efflux will come out to be square root of 600 or 10 root 6 meters per second. And once you get that, now you can see that rest it is falling through a height of h minus d, which is basically 10 meters. So the time for which it is in free fall outside is square root of 2 times h minus d upon g. So square root of 2 seconds. Okay. And therefore the range will be speed of efflux into this time. So it will be square root of 2 gd into square root of 2 times h minus d divided by g. So it will come out to be, or you can directly just see that it will come out to be 20 root 3 meters. So this will be the horizontal range. So you can also see one thing, that for a fixed value of h, which is 40 meters, if we take d as x as a variable, then we can find range as a function of x, and we can see that maximum range comes out to be how much? So the speed of efflux will come out to be square root 2 gx. Okay. And the range, which is speed of efflux into time of free fall, will come out to be this type of a formula. So we can see that speed of efflux is this sort of formula. Sorry, not speed of efflux, is the range. If we take d variable, then we can see that the range comes out to be like this, a function of x. So the maximum range will be maximum value of this function. Now this function, think of it like this. Okay. So this function has a maxima for x equal to h by 2. So the maximum range possible in this situation will be equal to h, and that will be when x is equal to h by 2. So we cut the hole exactly at the midpoint of the vertical wall, we'll get the maximum possible range. Okay, so this is a maximum horizontal range that can be achieved from this kind of a situation. Okay.
Sir, 1 minute.
Okay, so done with this now.
So just a minute, sir. Just a minute.
Sir, just a minute. It's not done. Sir, can you please scroll it down a bit? No, sir. No, sir. It's enough. Not done.
This is all there is in it. Okay.
It's not done.
Okay. So now another type of calculation that is done related to this efflux situation is calculation of total time taken to empty a tank through an orifice at the bottom. So let's say initially the liquid is there right up to the open top of the tank. This height is h. Okay. This cross-sectional area of the tank is A, and we have this small orifice which has been opened at t equal to 0. The orifice is opened. That is when the liquid starts to come out. And the orifice has an area small a. Small a is obviously very small compared to capital A. So at some general time t, the level of liquid would have come down in the tank, okay, because you're draining it out. So by now this level has come down to x or y or whatever. And accordingly the speed of efflux has also reduced. Okay, initially you can see the speed of efflux will be root 2 gh, but now at time t the speed of efflux is root 2 gy. So what is happening is that the volume rate of outflow, okay, volume rate of efflux, that you can think of as an instantaneous minus dv by dt, where v is the volume of water in the tank. So the instantaneous volume at this moment is k1. So that volume rate at which the liquid is coming out is the area of the orifice into the speed of reflux. So now substitute on this side the value of volume as cross-sectional area of the tank E into Y. And on that side, substitute the speed of efflux as root 2 GY. So we have the required equation that tells us that how Y is varying with time. It's varying in such a way that dy by dt is proportional to root Y. So if we integrate this relation, we can get Y as a function of time. So separating the variables, we can integrate it like this. So t equal to 0, the value of y was h. T equal to t, the value of y suppose becomes 0. So this will tell me the total time to empty the tank. So let's say that time I'm writing as something else, writing as capital T. So here capital T is total time to empty the tank. So note down this section and work out the integration. It's very simple integration. You can solve it with the limits and find out that this quantity, the time taken to empty the tank. Given that the area of the tank is capital A, the initial height of the fluid is h, and the area of the orifice is small. So in terms of those things, we'll calculate the time taken to empty the tank.
Excuse me, sir. Sir? Excuse me, sir.
Yes, what happened?
Sir, in the second beaker that you have drawn, in that V is equals to AY, then volume of liquid in what?
In the tank,
Tank. Okay, sir.
Yes, very good, Tantresh, that's correct. The final answer you got is correct. So hope the others have also worked this out. So the integration on the left hand side is 2 root y, right? But limits from h to 0 on the left hand side from 0 to t. So this will become minus 2 root h is equal to minus a by a 2 root g t. So time will come out to be e by a square root of 2h by g. You can see the time taken is going to be very large because that a by a factor is extremely large. Okay. So if we take a typical example, let's say h is 20 meters, g is 10 meters per second square, but the area of the tank is, let us say, it's maybe it's 5 meters square. Okay. Whereas the area of the orifice is obviously very small, so it's, let's say, 1 millimeter square types. You can see the time will be extremely large because of this. You can see that this will be seconds. So it will be 10 raised per 7 seconds. So even when you calculate it in minutes or hours or something, you will see it's a significantly large amount of time. And also what happens is that actually the rate at which the liquid is coming out starts to decrease very rapidly as the level of water comes down. So initially liquid will be gushing out at a high speed because the height is large, but as y starts to decrease, even the speed of efflux starts to reduce very significantly. So all that contributes to the fact that, so this is now, I've just taken a numerical example. So if these values are given, then the time taken to empty the tank.
Done, sir.
Okay.
So 1 minute.
Okay, so done with this.
Yes, sir.
Okay, now the final one more type of calculation that is related to this efflux concept is that when liquid comes out at high velocity due to efflux like this, it creates a reaction force. Just like when you fire a gun or a rifle, you experience a reaction impulse because of conservation of momentum. So that kind of thing. So that is called reaction force. Let's say F due to efflux. So the tank from which liquid is gushing out by efflux experiences a backward reaction force. And that can be calculated very easily by just using the concept that force is equal to rate of change of momentum and using the action reaction principle that every action has an equal and opposite reaction. So basic Newtonian mechanics kind of thing if we use. So now suppose, doesn't matter where I made the orifice, whether it's right at the bottom or somewhere on the side. So I'm just showing it for reference purpose over here. So liquid that is coming out at a speed, in general efflux speed, where that will of course depend on this height of liquid above the orifice. So that we already know. And if the liquid is of density rho and the orifice has an area small a, orifice area is small a. And what happens is that for a fluid element dm, okay, coming out or in efflux, okay, through the orifice in time dt, the impulse that is acting from inside is equal to the change in momentum. Okay. So this concept is that net impulse is equal to change in momentum. So for a small amount of impulse in a small time dt, we'll write it like this. Okay. So this tells us that the impulse acting is dm into v, because that fluid element is more or less at rest inside. Okay. So the force is rate of change of impulse or rate of impulse with respect to time. So that becomes dm by dt into v, where dm by dt is the rate at which mass of liquid is coming out. So dm by dt is density into volume rate. Which is nothing but area of cross section into efflux. So you can see that the force that the liquid is experiencing as it is coming out is this, or density into area of the orifice into 2gh. So the reaction force that the tank will experience will also be equal and opposite. Action reaction pair. Okay. So reaction force will also have the same magnitude. So this is again a direct formula that you should just remember, that if liquid of density rho is coming out of an orifice or an opening of area A at a speed v, then the force is equal to nothing but volume rate multiplied by density into speed. So that becomes density into area into speed squared. Okay, so with this we complete fluid mechanics now. Next chapter we'll be moving on to in the next week coming up will be properties of matter, in which we'll look at elasticity, surface tension, and viscosity, the three types of properties. Elasticity primarily being the property of solid materials, particularly metals or elastic type of materials like rubber, etc. And surface tension and viscosity are two properties of non-ideal fluids, okay, of real fluids basically. Ideal fluids are supposed to be non-viscous, or the viscosity is supposed to be negligible, as we've discussed before. Okay, people. So with that, we come to a conclusion of this section, fluid mechanics. Please work out the questions.
So I have to write that last one.
Yeah.
Excuse me, sir. How? I mean, I did not get the part where we got F is equals to rho into A into V square.
We just substituted dm by dt. In this formula, just substitute the value of dm by dt here. So we get this.
Yeah. Okay. Thank you, sir. Got it.
Okay, so people, that's it for today's session. Thanks for attending and wish you all the best.
Thank you, sir.
So